In today's lesson, we are going to be looking at the normal curve. So in the previous lesson, we looked at the probability distribution for continuous variables and we looked at uniform distribution. Now we're going to look at normal distributions, which is going to be the most common continuous distribution that we look at. It's going to be a little bit different because now we're not dealing with just a uniform kind of rectangle. So we have to come up with different ways to figure out the probabilities. So just as a little bit of a warm up, there are many continuous variables that are naturally occurring in the world and that result in the most amount of data at the mean and then data occurring in less frequency as you get further from the mean. So think of a continuous variable that would take this shape. You might think of it being called a bell curve, things like that. So think of things that you might find where most of the data tends to be around the mean or the average, with then fewer and fewer as we get farther and farther away. So if you can't think of any, that's okay. Right? In naturally occurring variables, we can assume that the modal interval rates for a normal curve will lie in the middle of the data at the mean, and then points fall above and below the average with decreasing frequency as they get farther from the average. Right? So you see an example here. Most of the data is in our modal interval here, and then there's fewer and fewer data points as we get further and further away from the mean, which is in the middle. Right, so the normal curve, right, it's also known as the bell curve. Data is distributed symmetrically and unimodally about the mean, right? So kind of that mound shape. Some examples might be rolling a die, right? Again, that's discrete probability or discrete data, but we see that the majority of data tends to be around 7. And then as we get further and further away, it's less and less likely to get each outcome. Right, if we're rolling 2 die. IQ. IQ tends to follow a normal distribution. Right, so if we look at IQ, most people tend to be around an IQ score of 100, with then fewer and fewer people being above and below. Birth weight, I've mentioned before, is a good one. Most babies born tend to be around this average birth weight, with fewer and fewer babies being born at weights above and below the mean. Or as we get further away from the mean, there's less and less babies being born at those weights. So when we're looking at normal distributions, and we talked a little bit about it before with percentiles and standard deviations, but we can use what is called the rule of 68, 95, and 99.7. So as long as the data is expected to be normally distributed, we can use the mean and standard deviation to calculate certain probabilities. And we mentioned before, because we have our mean in the middle, right? We have our mean in the middle, and we talked about within one standard deviation. So the mean plus one standard deviation, or you could say the mean, or you could just say plus one standard deviation and minus one standard deviation. So one standard deviation from the mean, we have 68% of our data. So that means that we have 34% from the mean and the mean minus 1, and 34% from the mean to the mean plus 1. If we extend a bit further, if we go 2 standard deviations away, so the mean plus 2 standard deviations and the mean minus 2 standard deviations, we go one more standard deviation, we find that there is now 95% of the data between those two ranges. So 68 is already within the first two, or the first standard deviation. Then when we increase further, we get 95. So there's 13.5 between 1 and 2, and 13.5 between minus 1 and minus 2. If we extend even further to 3 standard deviations away, 3 standard deviations away, so plus 3, minus 3, so even going even further, we now have 99.7% of the data between 3 standard deviations. So almost all of our data should be within 3 standard deviations of the mean. because we know what's already found so far, we can go and kind of use just calculations, difference, finding the difference. And there's 2.35% between 2 and 3 standard deviations on either end. And then in the likelihood that something exists beyond 3 standard deviations, again, it is very unlikely, but there's a 0.15% chance of it being above 3 and a 0.15% chance of it being below 3. So as long as we know, or if we're looking for values that fall on these specific standard deviations, we can figure out what probability, right? Because this is basically saying the area underneath this curve here is 34%. Over this entire section, it's 68%. So essentially that's what we're saying. So the probability of it falling within that spot is 34 or 68 or whatever each interval or each section happens to be. So we'll go through and kind of highlight those different intervals. Just so we can kind of get some color coding in here, see the difference. So again, here's the same thing a little bit. This one's a little bit more accurate with the different percentages we can see here. But I would stick to the ones that we kind of talked about, right? So 34, 13.5, 2.35, and 1.5. This is a little bit easier. So there might be a little bit of fluctuation depending on how you want to consider it. But again, for the most part, it's relatively the 68 between 1, 95 between 2, 99.7 between 3. So again, that rule is basically stating, so as long as we assume that it's going to form a normal distribution, right, then 68% of the data lies within 1 standard deviation from the mean. Right? So there's a 68% chance the data is going to fall within that 1 standard deviation. There's a 95% it's within 2, and a 99.7 it's within 3. So that's where that rule comes from. So we're only really focusing on these kind of variations. So, for example, the mass of potatoes has been found to be normally distributed, so that is key. So it's going to follow a normal distribution. The average recorded mass is 150 grams and has a standard deviation of 120, of 20. So that means if I were to look at an example normal distribution, we have one here. That means my mean in the middle is 150. 1 standard deviation away is 20 grams, so that means we have 170, and that's plus 1, minus 1, it's 130. If we go one step further, plus 2 standard deviations, add another 20, we're now at 190. On the other one, take away 2 standard deviations, we're at 110. And finally, if we add 3 standard deviations, that's another 20, so that's 210. It's minus 1 on the other end, so minus 3 standard deviations, or minus 20, we're at 90. So those are the different values we're going to be looking at. And when we're using the 68, 95, 99.7 rule, we're only really going to be focusing on variations of these because we know, again, 34, 34, 12.5, 12.5. If I go back up, I forget, 2.35, 2.35, and then 0.15 and 0.15%. So what is the probability that a potato falls between 130 and 170 grams? So 130 to 170, you could go through and it might be easy to kind of highlight, okay, what are we looking at? Well, we're looking at between the range here. So the area underneath the curve here would be 34 and 34, so 68. Because 130 is one standard deviation below the mean, and 170 is one standard deviation above the mean. So we're within one standard deviation, so that's 68%. The probability of our value being between 130 and 170 is equal to 68%. We could say 0.68. If I'm looking at the next one, B, 110, so the probability of my value is between 110 and 190. Right? If I wanted to highlight that, that is falling under these two sections. So what is the probability of the data point falling within that range? Well, again, the values that are being used is nicely between it's between two standard deviations. So this is nicely between two standard deviations plus or minus. We're talking about two standard deviations. That is a 95% chance. Right? So it is a 95% chance. We say 0.95. So there's a 95% chance that it will fall between 110 and 190 grams, because that's within two standard deviations. A random mass has a 99.7% chance of falling between what two masses? Well, we've already gone through and kind of done this. So 99.7 is anywhere from 3 plus or minus standard deviations from the mean. So this entire area is 3 standard deviations, 99.7% chance of falling within that range. Right, so the probability of it falling between, we have our low end 90. We say less than or equal to, again, doesn't really matter because the equal to doesn't change anything. So anywhere falling between 90 and 110, there will be a probability of 99.7 or 0.997. Because we're looking at basically 150 plus or minus 3 standard deviations for 99.7% chance. So that's really how we use the rule. And the nice thing is, all the examples that you look at, all the questions, it's going to involve these values. So it's very helpful to come up with a standard or a normal curve and kind of label out what 1, 2, and 3 standard deviations away from the mean would be. And you would be given that information. You would be given the average or the mean and what the standard deviation is. Otherwise, you wouldn't be able to really figure it out. So same example, given that x represents the random variable for the mass of potatoes and is approximately normally distributed with a mean of 150 and 120, we want to find the following. So it's going to be a little bit different. I'm going to go through and again quickly jot down the values of our potatoes, right, for the different standard deviations, 190, 210. Right, it might help again. So minus 3, minus 2, minus 1, plus 1, plus 2, plus 3. So I want to find the probability that a potato is less than 150. So again, it might help. Right? If I have my normal distribution, I have my mean, I want less than 150. I want everything on this side. Well, the mean is the middle, 150 is the middle. So that means that is dividing our data directly in half. So that means there is 50% that will be less than that value. Because we said before that in a normal distribution, the mean and the median are the exact same. So 50% of the data will be less than 150. So next one, less than or equal to 130. So again, if we want to kind of visualize, we already have our one over here, but just so we can kind of don't have to keep erasing it, we have something to look back. So here we have 150. 130 is here. That is minus 1 standard deviation. So we are looking for everything below that. So there's different ways you can think of it. You could go through and add up all the different possibilities, but we also know that the entire thing, or everything to the left of 150, is 50%. We also know that now that I'm 1 standard deviation away and I'm looking below that, from the mean to 1 standard deviation, that's 34%. So rather than adding up the three different groups, I could just say 50% minus 34% gives me 16%. So there's a 16% chance of the potato having a weight of less than or equal to 130. Right? So then that means then having a weight of 130 to 105 is the 34%, which adds up to 150, or sorry, to 50. The next one, the probability of a potato weighing more than 170. So this is very similar to the one we just did. 150. I'm looking at 170, which is 1 standard deviation plus, though, so above. And I want to find for more than. Again, similar idea, right? You could say, okay, well, above 150, everything above 150 has to add up to 50%, because that's the upper half. 170 is that mark for 1 standard deviation. So between 150 and 170, there's 34. And then everything above is going to be the difference between 34 and 50. So in this case, I can do the exact same thing. Everything above is going to be the same thing, 0.5 or 50% minus 34%, which gives us 16%. So there's a 16% chance of the potato, of a random potato, weighing more than 170 grams. And again, all the calculations we're doing, the main calculations we had to do was in the beginning when we created our values for the 1, 2, and 3 standard deviations away, and now we're just doing a combination of them, either addition or subtraction, and so on. What is the probability the potato weighs greater than or equal to 190 degrees? Or sorry, not 190 degrees, 190 grams. Right, so if we look at our distribution, right, normal distribution, we have 150. 1 standard deviation away is 170. 2 standard deviations away is 190. And I want to find everything above that. So above two standard deviations away. Right? So you think, okay, what's beyond that? Above, what's beyond? What is greater than 2 standard deviations away? If you go back up to your distribution table, right, you can add up the 2 columns. You could do 50% minus 34 minus the 12.5. Either way you look at it, or you could do the 2.35 plus the 0.15. Either way you look at it, you should get 0.25. 0.025 or 2.5%. So there's a 2.5% chance of it being above 190 degrees, or 190 grams. What about the probability of it being less than 190 grams? Well, we can still use the indirect method. If we know that above 190 is 2.5, Then below is going to be 1 minus 0.025. Or 0.975 or 97.5%. Right, so that would be the same thing that we just looked at. 150, 170, 190. Instead of looking above, we're looking at everything below. So we could go and add up each individual section from our normal distribution, from those 34, 12.5, and so on, or we can use the indirect method. Finally, the last one, probability the value lies between 130 and 190. So again, I'm going to draw it just to visualize it. So I have 150. I have 130, which is minus 1 standard deviation. I have 170, which is plus 1 standard deviation, and then 190, which is plus 2 standard deviations. So I want to find everything in between these two values. Well, between these two, because the first two are 1 standard deviation away, I know right now it's going to be at least 64%, or sorry, 68%. And then I'm going to add my little section from 1 standard deviation to 2 standard deviations, or 0.125 or 12.5. So then in the end, slightly, oh, not 12.5, my mistake, 13.5. So again, it does help. I'm kind of going off the top of my head, but it does help to go back and look at kind of these values, right? Because when I'm referring to adding different values, these are all the ones that I'm referring to. Those are all the values that I'm looking at, right? So those are all the probabilities that we're going to be playing around with and adding or subtracting. So it does help to have that on hand, as well as the different markers for the different standard deviations. So when I go through and add this up, I get 0.815 or 81.5%. So there's an 81.5% chance of our potato falling between 130 and 190 grams. Would the answers be different if the symbol used was greater than or less than, instead of less than or equal to? So would the answers be different? Right, so again, say we had the probability of a value being less than or equal to 130, or the probability of a value being less than 130. One is including the weight of 130, one doesn't include the weight. We talked about before, the probability of it being 130 is 0. The probability of being an exact value when we're dealing with continuous variables is 0. So either one, it's going to be the same thing. It's still going to be the same probability, because having that exact value of 130 doesn't make a difference. So having it equal 130 doesn't change the probability. So again, you could go and take out the equal sign. It doesn't really change anything. But the main thing from this is now we're looking at finding the probability for continuous variables that don't follow a uniform distribution. And we're looking at the very kind of basics of a normal distribution, focusing on the 68, 95, 99.7 rule, which uses the idea of a normal distribution and how the data falls in a normal distribution to allow us to determine the percentages or the probability of a data point falling under a certain section based off of standard deviations and the mean. So you'd always be given the mean and standard deviations and just have to kind of, again, use these values to determine the probability of a data point falling within a certain range.